For students sitting in the back, can you hear me? Okay, great. So remind you when anytime doesn't work. So I forgot my phone. So Sophia helped me use her Zoom link. I'm not sure if this recording is really recorded on this computer or recording in the cloud. So there might be a chance that we don't have recording of this class. So take good lecture notes. I'm not 100% sure. So today's last topic of the whole semester is a convergence study. This one is very important because I mean, when you use FEA and when you know that it's approximation, we definitely need to do the convergence study. And this is also one very important topic in your project. You need this one to work on project too. So the basic idea that, let's say if we have a real life situation, something like this. Of course, this is a very simple situation here. As you can see that we normally have fastener installed here and a fastener installed here. And these two fasteners is constraint or degree freedom, right? There should be no translation degree freedom in XYZ coordinate. There should be no rotational degree freedom in XYZ coordinate. So you can consider that whole bottom part is fixed. And this part probably is connected with other components. And when you do the free body diagram of this part or do the stress and density of this part, you separate this one. You separate this component with all the other structure and other here it becomes where the force applied by the other component. So you have the boundary condition, you have the force applied, you have the structure, and of course, and we can do stress analysis. And based on what we learned from the mechanics materials, actually we don't really need FEA analysis here. For this simple situation, we know that this is a bending situation, right? This is a clamped base and the force is applied here. It will generate a bending, and this becomes the moment arm. And based on our understanding of FEA of mechanics material, we know that the maximum stress is probably around this area. One thing is that, well, for the bending moment generated by this force, as it goes to downward, the bending moment increases and it's maximum here. The second thing is because in the real life situation, when you see something like this, it causes stress concentration, right? So we know that that's why we need to learn mechanics material before we start FEA. We know that probably around this area is somewhere we need to be more careful for finding the maximum stress. So for refining the mesh, we don't really need to refine mesh like everywhere. You know that refine mesh here doesn't make any sense. This is a clamped base. Refining mesh here doesn't make any sense. Refining mesh here, well, if you have force applied here, this part does not have any stress, right? And it's only between this one and this part. And you know that for this part, yes, it does have stress, but the stress, since the moment arm is much smaller than this area and also this part, well, you can just, based on your understanding from mechanics material, that the stress increase in this direction. So we know that if we want to save our computation time and get a more accurate result in the stress, the only area that we need to refine the mesh is around this part. So this is what in real life situation we did. First, we use a larger element size here. Now we use half of the element size and then half. And then now let's see the stress. The corresponding stress at these using 3 different mesh, and you can see that is gradually increase. So this is the basic idea of the convergence study. So when we know that for complicated geometry, for complicated loading condition and boundary condition, we know that there's no accurate analytical solution from mechanics materials. Mechanics materials, we know that, okay, for this structure, tension compression, I have accurate analytic stress, which is F of A. When there is a torsion, I know that TR over J. When there's a bending, I know there's MY of I. But not all real-life structure can be simplified as this one. When you see a more complicated structure like this, mechanical materials cannot solve it. So we can only use FEA. So FEA is basically, we describe into small elements. Each small element, we had KQ to F. we do assembly, and in this region, we know that it's high chance that it has maximum stress. We refine the mesh in this area, and then we see how it converge. So the basic idea is that we use large element size first and keep refine the mesh, and you see that different results, stress result coming out from Abacus or ANSYS, any software. And you probably could figure out if I take the half of the size, and if there's a great change in the stress result, it means that it's still far away from converge. It's still far away from the accurate results. But if you keep refining, let's say we can keep doing this, it's not just reset the data, you can keep doing it, and until time you take half the size, but the stress does not really change much. You know that you can stop there. There's no point like keep refining, and take longer time to run the software. So this is like, in the end, you can put all data, let's say y-axis is stress and x-axis is either the size of the element or number of nodes or number of elements, and then you can plot and you can see how it converge, and you can see the trend that when it's okay to stop and when it's not necessary to waste extra computation time. So this is the basic idea of convergence study. So this is in the chapter 9, section 4.2 in the textbook. So a simple plot, I can put it here. Either the x-axis is the element size or number of nodes and elements. Let's use element size here for H. So the y-axis can be either stress or displacement. You can try the project by yourself, like using different size and different number of elements or different number of nodes, and you can see how the stress generated from the Abacus. Probably what you will see that, of course, the refining process will start from a larger element size. There's an echo in the. This is the first data point, and then you're refining the element size, and keep doing it, and then you should be able to see a curve. So you should. Something like this. So this is the first 2 data points you tried. And you see, okay, there's not difference when you try different element size, but when you keep doing it, and around this point, let's say you try it again, this is the element size, and then you try another one, and if you like, okay, I change element size, the stress result, displacement does not really change much, and we know that, okay, it's get close to the convergence. We can say that we put a straight line, horizontal line here. This is the based on the FEA method is the exact value. There's no really analytical calculation of exact value, but based on FEA method, when you know that we see a trend here and it gradually converge to this value, this is the exact solution from FEA. But FEA, of course, itself is approximation. So element size is basically when you define the mesh, you can define the size, the edge length, everything. But when you read paper or read textbook, there sometimes you can see something like this. It's not based on the element size, it's based on number of elements or number of nodes, doesn't matter. So it should be very similar. And of course, when we do convergence study, we always start from lower number of elements or lower number of nodes, and then gradually refining. And in the refining process, the number of elements and number of nodes increases. And so same thing. Let's say at the beginning, you use this number of nodes or elements, and you get the corresponding stress results, and you refine it, and you see a huge stress or displacement result difference, and you know that you could continue doing it, and until around this point, let's say you try this number of elements or number of nodes first, and then keep refining it, and you don't see much difference in your stress or displacement result, and you know you are getting close to converge, and you can stop. So, and of course, you can consider this is the exact value based on our FEA method. And y-axis is still the stress or displacement. And x-axis now becomes number of nodes or number of elements. So this is like the most commonly see convergence study you will see either in textbook or paper you will read in the future. Mathematically, of course, we as engineer, we always want to simplify our process. We always want to use the minimum amount of time to get a result we want. So instead of like keep trying, let's say I skip the central part, instead of like keep trying, okay, use this element size and keep refining until at a point it converge. Actually, we do have a mathematical model that we only need 3 data points. I only try 3 data points, and I can calculate what is the convergence rate and what is the exact solution that we want. So let's say is the Richardson extrapolation. We have the we use a model. So UH is the corresponding displacement or stress result based on the size H. And U naught is the exact value we expect. And constant term, H alpha is convergence rate, and we have a high order or error term. I use alpha plus 1 here. So this is the model we have. And you can see that, well, let's put each parameter clear here. Is the exact solution. Or in these 2 graphs, I can actually put the U naught here to help you guys understand. This is normally something we are looking for in our convergence study. And G is a constant in the model, something we need to calculate. There's no physical meaning in it. Alpha is convergence rate. And of course, higher alpha means higher convergence rate. But most of the time, the convergence rate is between 1 to 2. convergence rate is greater than 1 and lower than 2. And in your project, of course, the convergence rate between 1 and 2 is based on the condition that you did everything correctly in the convergence study. And also, like different mesh, different element type you use may change a little bit. So in the project, if it's like a little bit higher than 2, you should be fine. That's not need to like exact between 1 to 2. So now the edge here is a very important parameter, is element size. And U sub h, the U it's just a result from abacus. It could be displacement, it could be stress. Don't just see U as displacement next node. This is just a separate mathematical model. U means whatever stress result or whatever displacement result you get from abacus, or it could even be the strain result if strain is your concern. So UH is displacement or stress result for element size edge. And the last term is the high order error estimate. And I add this term here just for complete of this equation of this model. And if you really like, you write MATLAB code and to run this, the whole thing, you can have this term. But for hand calculation of this for this semester, just imagine every term is already a much smaller term compared to the rest of two, and you have high order of a small number. It means that this term is much smaller than these two. So in our hand calculation this semester, in your homework, in your exam, in your project, you can ignore this term. But just for completeness of this equation, I put it here, but this one can be ignored this semester. Let's change the color. Now let's check this equation. Let's temporarily ignore this part and only focus on this part. We have, when you do the convergence study, you definitely know what is the element size you use, right? So in this equation, purely mathematically can consider this given information. And this is a result, either displacement result or stress result from the abacus. So you put in this element size, you generate this result from abacus. So this one is also considered as given information when you do the convergence study. And now let's say if we want to identify, this is something normally we want, the exact solution, we want to know this one or this one here. And this is unknown coefficient here. There's no physical meaning, just a coefficient in the mathematical model. This is convergence rate, we don't know. So now let's say for this equation, give information, unknown, unknown, unknown. We have 3 unknown information in this equation. So we need 3 set of data, right? So basically, when we use this model, it means that if we have 3 set of data, we can get what we want. And also sometimes if you need convergence rate, you can find this one. This one you can calculate, but does not really have any physical meaning. So this is why I said to save you some time and effort after you graduate. Let's say you become a structural engineer, you do FEA analysis. Instead of like keep trying, okay, choose here and then here and then here and then here and then here, and spend your whole day running the FEA analysis. You can only have 3 set of data and use this equation, and you can calculate what it is. The exact solution here, or exact solution here, and you're done. So this is the whole purpose of our topic today. So we only need 3 set of data. So we have 3 unknowns. And it only requires 3 set of data. Another thing I want to emphasize here, so if you have a trust problem, like trust structure, and that one probably should be fine, because for trust member is tension compression. It's just like each trust you have 1 element, you should be fine. Increase the number of elements does not really change the results, because tension compression itself is already accurate. You use 1 element, you use 10 elements, it's always sigma equal to F over A. So let's say now when we change to something more like plane stress, you use triangle element, you use quadrilateral element, you use 6 nodes, 8 nodes, 4 nodes, 3 nodes. Now we need to know that the element size, what does this element size really means? Because I mean, for a rectangular element or triangular element size could be area, could be edge length. So, and also let's say when you go to 3D, you cannot really simplify everything in real life structure as a plane stress or plane strain as 2D problem. There are a lot of problems you need to deal with. They are 3D. So in that situation, we may use like cubic element or tetrahedral element. And in that situation, I mean, what the element size means is volume or edge size. So here in the, if you read textbook, there's really no clear definition of the element size, which confuse a lot of students in the previous semesters. So here I just want to emphasize here, the element size is always the edge length. No matter it's 2D, 3D, no matter you are using the triangular element, quadrilateral element, or tetrahedral element, anything, any type of element size does not represent area or volume or anything else. It's only the edge size, the edge length. And this concept is very important for your calculation later. Any questions so far? So now we have the equation, we clarify all the parameters, and we know that we need 3 sets of data. Now let's assume that we have 3 sets of data. We normally, let's say the first try, you use H1, and then you find the element H2 and H3. And of course, you get a corresponding UH1, UH2, H3. And of course, normally when we refine element, it means that H1 greater than H2 and greater than H3, right? And so normally when we do only use 3 sets of data, what we normally do that to simplify the calculation, we use the same ratio. So H3 equal to P, H2 equal to P squared H1. So the ratio between them is a P. And this ratio is normally smaller than 1, of course. Is equal to H3 over H2. H2 over H1. This is like most time we doing this way to simplify our calculation, but of course you can do a convergence study that H3 over H2 is not equal to H2 over H1. It's perfectly fine. It just takes more time to do the calculation. Sorry? Yeah. So what do we normally do? Let's repeat it here. What we normally do that we use the same ratio H3 over H1. Since it's a refining process, so H3 is smaller than H1. Make sense? So the ratio of H3 over H1, this p-value should be smaller than 1. And we use the same ratio for H2 over H1. We commonly do this, use the same p here in the refining process to simplify our calculation, but of course, you can use different ratio here. So now we have H1 to 3, and you put in the abacus, you have the UH1, UH2, UH3. So we have 3 sets of data. You just need to use these 3 sets of data to calculate the 3 unknowns. So now it becomes pure math. For UH1, UH2, H2 alpha. And since we have the ratio P defined, plus G P alpha H1 alpha, because H2 equal to H1 times P. So I write it as P H1 alpha. So now you compare this equation and this equation, it has both the H1, both equations convert to H1 here. And similarly for H3, we have H3 alpha, and we have G2 alpha and H1 alpha. Now let's use the second equation minus the first equation and the third equation minus second equation. We can calculate the convergence rate. Sometimes it requires us to calculate convergence rate to see how it converge. And we have the UH2 minus UH1 equal to G. So now we have, we take a ratio of these two. Now you can see that we have G here, and this part is also the same. So UH2, UH2 minus UH1. This ratio is equal to P of alpha. And now when you see this equation, of course, this equation you can use in project, in exam. I don't think I assign homework related to this part, but it may be happening in the exam. So these are the given information, UH1, UH2, UH3, they are the given information. P is the ratio between the element size, is also considered as given information. So in this equation, you can use directly to calculate convergence rate. That's the whole point of derivation here, right? And now, of course, another goal is calculate U0, the exact solution. So let's do one more step. Be patient. In the first equation, we multiply by H2 alpha on both sides. So we have U0 H2 alpha, G H1 alpha, H2 alpha. And the second equation, we multiply by H1 alpha on both sides. And now you can see from these two equations, when we multiply by h2 alpha on both sides of the first equation and h1 to the power of alpha on second equation, you can see this term to cancel. And we can calculate the u0. So now you check this equation. P is the ratio of the element size. Alpha is the convergence rate that you probably can calculate from this equation. UH1 and UH2, they are when you put in H1 and H2 in the mesh, and they are the result generated from the abacus. So basically, you can use this equation directly to calculate our exact solution based on the FEA method, right? So this whole derivation part, it may look boring, but it's really the basic idea is very simple. We have equation, we have a model with 3 unknowns. We need 3 set of data to solve the 3 unknowns. So basically, plug in the 3 set of data and do some simple derivation, you calculate 3 unknowns. But of course, you can ignore all this part. You just do the calculation by yourself, right? Because if you have 3 set of data, you have 3 unknowns, you can use your own method to calculate 3 unknowns. I don't really care like which method you use. But if you want to use the equation we derived here directly, you can use this one directly to calculate convergence rate. You can use the equation here directly to calculate the u0. Depend on you, whichever you prefer. So any questions so far? Okay, let's do an example problem. We need to use a square element to model a rectangular block. And of course, the rectangular block is simplified as a plane stress situation. So let's say we try 3 set of data. We have the number of elements, number of square elements. First, we try 100, and we get displacement result. And then we try 400 elements, refine the element, and the number of elements increase 400, and this is a displacement result. And the third iteration, 1600 elements, and this is a displacement result generated from software. And of course, the question is calculate convergence rate, calculate exact estimate exact displacement. How to calculate convergence rate, how to calculate the exact displacement. This is a very straightforward application, right? We have everything derived. So convergence rate here. UH1, UH2, UH3, they are given. So the first thing we need to figure out what is the P here. 4. Right. Why P equal to 4? How about, okay, I guess this one also equal to 4. Any other opinion? Thank you. Any other opinions? What should be the P here? What should the P here? Just guess. I mean, it's fine. What? 3? Why 3? You need to give me a reason. Yes, it's not a reason. Any other opinion? What? Why?
Well, you do 100 divided by 4.
Okay.
And it needs to be less than 1. Be less than 1.
Yes, P less than 1. That's very important information here. Yes. So because P is less than 1, yeah. So any other opinion? What should be P? So anytime you feel confused, you always go back to the basic concept. What's the definition of the P here? That's why I emphasize the P is the ratio of the H, and H is the edge length of each element. So anytime you feel confused, always go back to the basic concept, the basic definition. So give you another chance. What is the P here? Anyone? Yeah, yes, P is the ratio. Yes. What is it? Give me a number. 100 to 400 to 1600, but this is the number of elements. P is a ratio of edge.
Do we not have the actual edge length? We just have a number of elements, so do we just leave it as P to the alpha? And
P to the alpha?
Fine, do not.
Here, this side is the displacement result. So we consider this is given information because this is the, let's say, this is the UH1, UH2, UH3. We can calculate this side.
Okay.
We need to find this P before we calculate convergence rate. Convergence rate is also unknown. So we need to find the P based on this one first, and then we can calculate convergence rate. So the question now is, what is the P? One-fourth. Your explanation part is correct, but let's calculate in this way. Yes, we are modeling the same structure, right? So for the plane stress, the same structure should have the same total area. Make sense or not? Let's assume that the total area of the structure is A. Now we know that definition of the P is when we're refining H2 of H1. So what is H2? For the total area A, we use 400 elements. So this becomes the area of one element. And we are using square element. What is the edge length? Yes, thank you. And when we model using H1, we are using 100 elements, right? And this is the area of each element, and the edge length equal to square root of this one, since we are using square element. And now this is the ratio P here. Any question here? It's the same. So for the triangle element, probably like area is equal to a coefficient times the edge. Let's just use L squared, right? And then when you take the ratio, this coefficient is gone. No matter it's triangle element or other different shape, yeah, it doesn't matter. Including like if you use tetrahedral element, let's say you assume that structure have the same volume, and the edge length, let's use L cubed, and there's a coefficient in front, and the coefficient cancels out in the calculation. So in the end, if it's a 3D, if it's 3D, then it becomes the ratio we consider, let's say V over, let's still consider as 400, but right, because let's say if you use a cubic element, then V equal to edge length cube, right? And if you tetrahedral, I guess the coefficient 1/3, but in the end, cancel out. Yeah, so it doesn't matter. Yeah. Any other question?
What if they're differently shaped?
Combination of square element and triangle element, we normally don't do that. In real life situation, it's like as an engineer, we decide what element type we want to use to be most efficient and most appropriate for our application. And we normally use one type of element to model the whole problem. We may have combination of different size in the critical area, like in the area that we don't care, we use larger element size, and in the area that you know that it would have the highest stress, use in that area, use more element, but we normally do not use like combination of triangular element and quadrilateral element. Yeah. So this is the p-value. Let me quickly finish this part. For the rest calculation is simple. Since we have these two equations, we just use these two equations directly. This one to calculate alpha, and we use this one to calculate U naught. So here UH3 minus UH2. And UH2 minus UH1. And we already know the ratio P equal to 1/2 and alpha. And we can calculate alpha here equal to 1.47. It's between 1 to 2. And the exact solution from our FEA approximation is equation is here. I will plug in the numbers directly. One half to the power of alpha convergence rate. Well, let's move the original equation to this side, so you guys not get confused. So the key thing here is to figure out what is P. Once P figure out the rest part, well, just plug in. This is UH1, UH2, UH3, right? And the first part is just calculation. Any question here?
The same units are displayed.
Yes.
But alpha is unitless.
There's no unit for alpha. It's convergence rate. Yes.
Can you just make the elements like super large and will this still
Yes.
hold true?
Yes. Then you need to check the convergence rate. If it's not between 1 to 2, you probably redo it. Yeah. Sorry, I'll do it.
triangular elements versus square elements?
Triangular element we talked about in chapter 6 is similar, is constant strain triangular element if we only have 3 nodes. So if you want to save some computational time, triangular element definitely can model faster, but it loses some accuracy because it's constant strain, constant stress.
Okay. You thought the ROT bigger than like every other.
Great question. Let me be patient a little. Wow. Let me check the time. I will try to explain within 1 minute. So stay quiet. Great question. So yes, U naught will always be greater than UH1, UH2, UH3 because when we do the convergence study, it's always converging from below. And the reason is that we know that when it is in a situation that FEA can only do approximation, what does approximation means? We only use lower order of polynomial to model a higher order that is supposed to be, right? Let's say we talk about in Bean chapter, if you have a distributed force applied, if uniform distributed force should be 4th order, but you use cubic polynomial to model that one. If the linear change distributed force, it should be 5th order, but we still use cubic polynomial to model that one. So we are always using, when it's approximation, we are always using a lower order polynomial to model something that is supposed to be higher order. So in this process, we are losing some flexibility because lower order. And losing the flexibility means that K, Q to F, the Q is lower than the exact solution. And when we convert Q to strain, strain is lower than exact solution. When you convert strain to stress, stress is lower than exact solution. So in the convergence study, it should be always converging from below, which means lower, higher, 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 higher. Yeah, great question. Thank you.